All right, it's two now. Let's get started. So thanks for coming to the Ask seminar series. This is John. I'm the seminar coordinator, so I will be moderating this seminar with Jennifer Cullen, who is our communication specialist. Just so you know that this talk is being recorded, and we will publish the video recording on our YouTube channels. And after the speaker's presentation, we'll have a Q&A session, and we encourage you to speak up and bring up any questions you may have. You can, if you don't have a mic, you can also chat us questions, and we will read them out. And our director, Nas Peter, also joined us. And I'm going to hand the ball to Nas to introduce the speaker. So Nas, please go ahead.
Yeah, thanks, John. And hello, everybody, and welcome to today's ESSEC seminar. And it is my pleasure to introduce today's seminar speaker, Professor Gary Lackmann, who will be talking to us about geohazard connections in a warming world. This is a very interesting abstract linking various domains in the Earth system together and giving us maybe some new insights in how these things play together in some hazardous events. Gary is with NC State. He's a professor in the Department of Atmospheric, Earth and Marine Sciences, and he is also the head of the department there, teaches meteorology and NWP. Gary got his bachelor's master's degrees from the University of Washington and followed by a PhD at SUNY Albany and has now been at NC State for just over 25 years. Before coming to NC State, he had stints at PMEL, the Naval Postgraduate School in McGill, and a faculty position at SUNY College in Brockport. He has received a long list of awards for both teaching and research and editor's work, and I'm going to skip lightly over them and just mention that Gary is an AMS fellow and a former AMS council member. With that introduction, Gary, over to you, and we look forward to hearing what you have to tell us.
Great. Thank you for that introduction, and thanks for the invitation to speak. I'm excited to share some work. As Lars mentioned, I'm kind of in an administrative role now, so it's a real luxury to be able to give a science talk. And I'll be talking about some personal experiences from both coasts. Let me see if I can get the slides to advance here. I guess as probably most of us were aware, starting in 2023 in July, the ocean surface temperatures just moved into record territory. And if you look at this is from the Climate Reanalyzer website based on the NOAA OISST website. There's the last 2 years going through 2024 were far and away the warmest on record. And if you look globally, you see that this SST anomaly from the 91 to 2020 baseline was widespread. And in the North Atlantic in particular, it was in record territory as well. And I should point out that this is an ongoing ocean extreme event, with the current year being in third place next to 2023 and 2024. So if it hadn't been for the previous 2 years, we would be in record territory right now. So see, I do want to check the chat and make sure that people can hear me okay. I don't see the chat on here. Is everything coming through okay?
Yep, we can hear you.
Okay, great. So why is this happening? There's a lot of literature coming out about this. some of you may be involved in some of these studies. Is this an acceleration of anthropogenic greenhouse gas-driven warming? Is it due to the 2020 shipping fuel and emission policy? Was it the Hunga Tonga volcanic eruption injecting water vapor into the stratosphere? Is it related to INSO? There's studies looking at cloud cover anomalies. Other studies have attributed it to natural variability. We're in the active sunspot phase. So there's a lot of papers coming out looking at this record event and looking at the different causes. There's a really nice website from Berkeley Earth where they sort of look at several of the different proposed forcing mechanisms for this, and they kind of quantify, they look at the different time scales. It's quite interesting. And the paper that I like is Chamberlain 1890, The Method of Multiple Working Hypotheses, where Chamberlain points out that it's in the Earth system, it's rarely one thing that's the cause of some extreme event. He uses the Great Lakes as an example for where there's several different factors that contributed to the formation of the Great Lakes. But if you look at the different studies, there's strong evidence that these records would not be happening were it not for the global warming trend. There's internal variability definitely playing a role. And then a lot of studies looking at the shipping emissions policy change and how that changes the radiative balance. But probably it's, at least in some part, all of these factors. But so we have an ocean extreme event that's lasted a couple of years now. And what are the implications of that? Well, as an atmospheric scientist, when I see warm water, I think high dew points, and the atmospheric water vapor concentration is essentially dictated by the sea surface temperature through the Clausius-Clapeyron relation. And so that would say that record sea surface temperature warmth implies record levels of atmospheric water vapor. And so if you look at the global monthly precipitable water, which is basically the total of atmospheric water vapor, we see that it looks a lot like the sea surface temperature curve. And these last 2 years have been the highest on record, and not just by a little bit, by a considerable margin. So by the time we got to coming into September of 2024, there had never been more atmospheric water vapor. At least, I shouldn't say never. In fact, almost certainly that isn't true, but over the period of the ERA5 reanalysis starting in 1940, there hadn't been more. So why does that matter? Well, I love this paper by the famous mathematician and atmospheric scientist Michael McIntyre that came out in 2022, where he says, water vapor can reasonably be called weather fuel because of the latent energy released when it condenses. And he says, global warming is global fueling. And with this analogy, the gas tank had never been more full than it was entering September 2024. So, the role that water vapor plays in certain types of extreme weather event suggests that it has an amplifying capacity for some kinds of weather extremes. And so when you have an extreme oceanic event like the one ongoing, that's going to be associated potentially with amplified extreme weather. So if we look just in the southeastern US, I'm here in Raleigh, which is right here, but we had potential tropical cyclone 8 on September 15th and 16th of last year. And this shows the MRMS precipitation accumulation. And we had over 20 inches of rain in a short period of time down here in Brunswick County, which is near Wilmington, North Carolina. There was extreme flooding, road washouts, it was a major event down there. But the storm itself didn't acquire enough strength to earn a name. But if you look at the return period, using something like Atlas 14, this was a 1,000-year event. But no one talks about that because just a few weeks later, we had Hurricane Helene. And out in front of Helene, there was this predecessor rain event, or pre, that dropped over a foot of rain before Helene was even up to the latitude of Tampa. And so there's already flooding and saturated soils going on in the southern Appalachians. And then Helene got there and brought even more intense precipitation, strong winds on saturated soil, strong orographic lift. So that was another 1,000-year event. And so we had, in the state, we had 2,000-year events in a 2-week period. And then, of course, shortly after that, we had Hurricane Milton, which was a very impressive tropical system in the Gulf of Mexico. And so this was all sort of in rapid succession last September into early October. And I'm not saying that these events were entirely attributable to the extreme oceanic warmth. I mean, we have had strong storms like this in plenty of other years, but the excessive precipitation, perhaps the extreme deepening rate, these are things that can have some influence from stronger than average condensational heating. So if we look at sort of the sequence of events, we had this extreme oceanic event that fueled up the atmosphere. Then we had a series of extreme atmospheric events that led to other hazards. Some of those impacts included extreme hydrological events. Here's Interstate 40 getting washed out by the Pigeon River in western North Carolina. This shows the map of fatalities associated with Hurricane Helene. And they weren't concentrated at landfall. They were concentrated up in the mountains of North Carolina, hundreds of miles inland. This is from the USGS. This shows the landslide activity in the southern Appalachians. There are over 2,000 documented landslides by the USGS, and the ones that are flagged cause damage to some road or structure, so over 1,000 of them. And a number of those are associated with significant fatalities as well. Because the ground was saturated and the storm was still packing hurricane force gusts at the higher elevations, there was extreme blowdown of trees, especially on the windward slopes, as evident in this picture. And that is fuel for wildfires, for forest fires. And so if you look at kind of the predicted fire danger from March of this year, it aligns pretty well with these areas where the tree blowdown occurred. And then, of course, that's been manifest with a very active wildfire season. This is partly exacerbated by the drought and the dry weather we've had. So that is another impact. And the other thing that the geologists in my department, the geomorphologists in particular, point out that a large fraction of the landslides with Helene were triggered at roadways. And that is very interesting. There's mitigation possibilities there, but that's another interesting fact that has come to my attention during this sequence of events that's ongoing. We still have had fires even recently. So we had extreme ocean warmth that led to record values of water vapor, which then helped fuel these extreme precipitation events, which led to extreme hydrological events and geological events and bioecological events, which has led to fire weather and ultimately air quality and human health hazards. So if you spoke to people out here in Transylvania County or Henderson County, North Carolina, that had very unhealthy air quality, and you said, this is really because of warm ocean temperatures, they would probably ask for a more detailed explanation for how those connections work. But these are some of the things that we're thinking about with the interconnectedness of the different parts of the Earth system. The geologists in my department are interested in just the total amount of mass that moved in those landslides, and how much does landscape evolution relate to extreme events like this, and also how many people, how many homeowners, how many people were at risk from those landslides that were living with a landscape risk that they were not aware of until this event triggered the landslide or mud flow. So this is intriguing. This is kind of a recent event. I'm not going to get into Hurricane Helene further. There's a lot of research I would like to do with Helene. I would like to know things like, well, how much rain would have fallen if Helene hadn't come along just from that predecessor event? And also, what would Helene have looked like if it were kind of a normal climatological SST year? How much of the additional precipitation was related to that? But I'm going to switch coasts and talk about an event that I've had more time to study, and that's the June 2021 Western North American heat wave. And again, looking at this idea of physical process connections, how those connections might change in response to climate warming, and then thinking about the implications for the frequency and intensity of extreme events more generally. So that's the idea. So we're jumping from the East Coast to the West Coast. I grew up in Seattle, Washington, and here's Vancouver, British Columbia. And I've circled the small town of Lytton, British Columbia up here. This is the Fraser River Gorge in British Columbia. And Lytton had quite a week on the week of June 27th, 2021. So on the 27th, they broke the all-time Canadian high temperature record of 47 Celsius, 116 Fahrenheit, which, given their location kind of in the heart of the Canadian Rockies, is pretty impressive. But then the next day, they did better and they broke the record again, coming in at 118 Celsius. And then on Tuesday, the 29th, they broke the record again, hitting nearly 50 Celsius with 121 Fahrenheit. I should point out, this is the warmest surface temperature recorded north of 45 degrees latitude even. Just a remarkable off the charts kind of event. But they weren't done yet, because then on Wednesday, the 30th, they evacuated Lytton. And then the next day, 90% of Lytton was destroyed by wildfire. The extreme desiccation associated with this heat led to a devastating wildfire that swept through the town. And if you look at their wiki page, I was trying to figure out, how much rebuilding has occurred since then. They're still in the process of rebuilding. A lot of the town looks just like slabs, and they have not rebuilt at this time, but they're working on it. But it was a devastating event for that community. But more broadly, this event is associated with over 1,400 fatalities. This event is the deadliest weather event in Canadian history, with 808 excess deaths and 685 confirmed fatalities. And this event is maybe one of the most studied meteorological events of our time. There's just dozens and dozens. I submitted a journal paper about this event, and it was, every time I would get ready to submit it, I'd have to add in more citations, because so many people have studied this case, because it was just such a remarkable event. You're looking at Portland, Oregon. If this chart shows January through August, but the kind of gray lines in the background, those are the previous record highs. And then the climatological temperatures are shown with the darker gray for the highs and the lows. And if you look at this event, the 3 days that Portland set a record in June 2021 are so far off the charts for any other record high temperature that was set. That just was meteorologically intriguing. And my parents out in Seattle, sometimes they say, "Oh, Gary, how can you stand the heat that you have there in the summer in Raleigh?" And I say, "Well, Seattle's been hotter than Raleigh's ever been." So Seattle SeaTac Airport has a higher all-time record high than Raleigh does. And even over on the coast, Quileute hit 110 Fahrenheit, and their previous all-time record had been 99. So this event was really just a remarkable occurrence. So how did this happen? On the left, we have the 500 millibar height and eddy height shaded. So we had a really strong upper level anticyclone. At the surface, sea level pressure is shown with the colored contours. We had a high inland, we had a low on the coast. I should point out at upper levels, there was this upper level trough to the south and west of the anticyclone, and that was probably helping to lower the pressure in the coastal areas here, which helped drive that offshore flow with compressional downslope warming to the west of the Cascade and Olympic Mountains, and bringing the heat into places that don't ordinarily get it. So that was remarkable in the kind of upper level setup. But I was interested, scientifically in what were kind of the precursor processes that amplified that upper level ridge. That's been studied quite a lot, so I'm not going to focus on that. There's probably 6 or 7 studies that I could cite that would talk about the development of that block. So what I'm going to talk about today that's a little bit more unique is the role of a Chinook or Foehn type mechanism in this event and why that matters in this case. I just had something pop up on my screen here. Hopefully you're still seeing that presentation okay. So we did some simulations with the weather research and forecasting model, and also analyses with the GFS and the ERA5 analyses and reanalyses. I did 7-day simulations where I initialized on 0Z the 22nd. I did a number of different experiments. I'll show those. We did another set of simulations with a higher resolution nest over the Pacific Northwest and Canadian Rockies into Southeast Alaska to see if the resolution of the topography made a difference. And I won't talk about all of these experiments that I did, but I did some experiments to sort of test this idea that there was a Chinook or Foehn type mechanism. So in terms of the upper ridge, I will just talk about that briefly because that was such a critical aspect of this event. This map, the color shading is potential temperature on the dynamic tropopause, the 1.5 potential vorticity unit surface. So the warm colors show where there's anticyclonic potential vorticity aloft, and the cool colors are where it's cyclonic. The purple contours show column integrated condensational heating. And then there's winds on the dynamic tropopause shown with the wind barbs. So you can see there is this sort of injection of condensationally heated air that's wrapping anticyclonically into this upper level anticyclone. So this is an anticyclonic wave breaking event that's being fueled by condensational heating. Very heavy precipitation was falling along this axis and in the mountains of Southeast Alaska and British Columbia. So kind of the upper level anticyclone had condensation helping fuel that anticyclonic rotation. This is what Steinfeld and Fall and others have called a moist diabatic block, where you're looking at moist processes as being critical to the intensification and maintenance of the upper level anticyclone. I did some potential vorticity budget calculations in the area where this condensational heating was occurring. And as you would expect, there's The blue shading shows anticyclonic potential vorticity tendencies above and cyclonic below, and that's consistent with building the upper level anticyclone above the level of maximum heating. So that's all pretty well established, and there's other studies that have looked at that. One thing that was interesting, if you look at the sea surface temperature anomalies during the formation of this upper level anticyclone, there was a very large area of warm sea surface temperatures over the eastern North Pacific, a lot of the North Pacific, to the tune of 1 to 3 Celsius anomalies. And the kind of condensation upstream of this anticyclone likely involved air that was moving over these anomalously warm waters. Satellite image from that time period shows what we would call an atmospheric river, warm conveyor belt. There's warm, moist air flowing northward, and then condensational heating along the axis, but also strong orographic, heavy orographic precipitation in Southeast Alaska and northern British Columbia in the Coast Range. And so it's likely that these air parcels have interacted with this warm sea surface temperature anomaly. So that leads us to the next question, which is, well, okay, well, where did this anomalously hot air come from? I mean, these temperatures are off the charts. What caused that air to attain that kind of warmth? And that's where I'll explore. And I'm not saying that there's just one mechanism, but let's take a look. So I don't want to insult anyone's meteorological intelligence, but I'm going to break it down with some really simple meteorology. So I appreciate your patience. But the Chinook or Foehn, the kind of traditional mechanism for a Chinook or Foehn flow is you have an air parcel on the windward side of the mountains, and it rises. And once you hit the condensation level, then you're releasing condensational heat into that air parcel. So it cools at the dry adiabatic lapse rate. And then after that, it cools at the slower moist adiabatic lapse rate due to the release of latent heat. But then as soon as that air parcel descends, it immediately becomes unsaturated because you've precipitated out the vapor, and it compresses at the dry adiabatic lapse rate and attains a temperature that's much higher on the leeward side than at the same altitude on the windward side. And so this is sort of a classic mechanism for the Rockies in the winter. And there's a lot of studies going back to the 1800s that have talked about this. So it turns out, though, in the Foehn literature, especially in the European community, this kind of condensation is really sort of one of the many mechanisms. They also talk about isentropic drawdown, where when you have westerly flow over mountains, a lot of times you'll just have high potential temperature air from aloft descending and compressing in the lee of the mountains, and that can contribute to the warmth in the lee. Because of the dryness in the lee due to the orographic subsidence, that's favorable for radiational warming. And then also, depending on the flow, you can get turbulent mixing that deepens the boundary layer and also mixes higher potential temperature air to the surface. So in the modern Foehn literature, they view the warmth in the lee as not resulting just from the condensation. That's kind of the traditional mechanism, but these other mechanisms that should be at work as well. So how would that work in this case? Well, we wanted to do some trajectories. That's a great way to check where that air came from. And a shout out to my graduate student, Lauren Getker, who really did great work getting Lagranto to work. And the Lagranto package, software package, comes from ETH and Wernley and Davies 97 and others. And there's Worf Lagranto, and Lagranto is able to work with ERA5. It's a really nice trajectory data set, trajectory software package. And so we started back trajectories in the lower troposphere in the heat wave region. And we kind of basically took the hot air and ran 400 backward trajectories back 6 days, kind of from the boundary layer in the lowest kilometer of the atmosphere, so that we could see where that air came from. And I would wager if you talk to Seattleites during this event and said, where do you think your air, this hot air came from on this record-setting day? Do you think it came from Arizona or Alaska? I would imagine most people would pick Arizona, but they would be wrong because virtually all 400 of those trajectories came from Alaska. So that's not where they originated, but that's where they had been most recently. And this shows, we were using the WRF model data for this. We have other trajectories that we did with ERA5 that are very similar. But because our WRF boundary didn't extend far enough west, some of the 6-day back trajectories were outside of the domain at day -6. But these trajectories are shaded by pressure. So the ones that are dark blue are in the upper troposphere. The ones that are red are in the lower troposphere. So you see that there's sort of different classes of trajectories. There's one group, the ones that start out with the red and orange colors, they're starting in the marine boundary layer north of Hawaii, and they're moving northward in this atmospheric river and then lifting over southeast Alaska, northern British Columbia, and then turning anticyclonically and descending into western Washington. There's another group that starts at high altitude and higher latitude mostly, and they tend to cool, their potential temperature tends to cool. So this is sort of the isentropic drawdown group. And then there's a third group that kind of starts at mid-levels and mostly conserves theta throughout their 6-day history. So that was interesting. We can make this transparent to kind of see through it a little better. So kind of the Chinook type setup here is not a traditional Chinook. You start out over the Pacific, then you get lifted over the Alaska coast range, then you loop around anticyclonically and descend on the west side of the Cascades or Olympic Mountains. So not your kind of classical Chinook setup. And then there's also subsidence east of the mountains into, so like Lytton, British Columbia would be like in this situation. So there's kind of a more complicated than usual Chinook scenario, if that's even what it is. So we looked at the trajectories and kind of these different groupings with a heat map. So these 3 panels, the top panel, so the kind of the ending of the trajectory in the lower troposphere is at time 0 on the right, and it goes back 6 days to the left. And the top panel shows potential temperature, the middle panel shows pressure, and the bottom panel shows relative humidity. So if we look at the, at day -6 to say day -4 and 5, a lot of these red trajectories, they started off with low potential temperature at relatively high pressure and with high relative humidity. So those are going to be the kind of Chinook-like trajectories. Then there's other ones that started with higher potential temperature and actually cooled slightly. These are kind of the upper tropospheric isentropic drawdown ones. And then in green, there's the ones that approximately conserved theta within 5 degrees. But you see in a lot of these, there's also the sort of stair stepping you get the last couple of days that implies radiational warming. So I think we see evidence for isentropic drawdown with the blue trajectories, radiational warming with sort of the stair stepping, and then condensational heating with the parcels that start moist and end up drier. And so we can make this transparent. In case you're wondering where all these red trajectories went, if I make the heat map semi-transparent, you can see that those red trajectories sort of blend in with the other ones and then wind up over here at time 0. So it's complicated. It's not a pure Chinook type flow. There's evidence of multiple processes here, but there is some support that enough of these trajectories, about almost half of them, experience a significant warming of potential temperature and also drying of their humidity and kind of low, high, low altitude changes. And so we can do some statistics with these trajectories. And we find also, if we look at the warming trajectories, 95% of them were associated with non-zero cloud water at some point in their 6-day life cycle. So that's also consistent with a Chinook type flow. So in terms of a kind of simple exercise, if you look at the GFS analysis or the ERA5 reanalysis, and you take those trajectories that started north of Hawaii, the ones that started out here, and you kind of look at the temperature and dew point conditions, it's around 25 Celsius, around 75% humidity. Here's the pressure. If you take that air and lift it to 650 millibars, which is about how high those trajectories went over the coast range, and then bring it down dry adiabatically, you find that 8 grams per kilogram of water vapor condense. The final temperature on your SKU-T chart is 41 Celsius, which is reasonably close to what was observed in Western Washington and Western Oregon. So if you just take this amount of condensate and use the first law, you get almost the same amount of heating as what you get with this SKU-T exercise, except the difference is that the initial pressure was a little bit higher than the final pressure, so you don't realize the full compressional warming, but it's pretty close. And that makes it look like this mechanism could help explain the extreme heat that we see. But I wanted to do a little more to test this hypothesis. And I think there was this upstream atmospheric river that we saw in the Gulf of Alaska. And so to sort of test this mechanism, if we weakened that upstream atmospheric river or dried the upstream flow, then that should predict cooler temperatures near the surface during the heat wave over Washington, Oregon, and British Columbia. So we can use the model for this, or we can just turn off latent heat release, which is a heavy-handed approach. So here's the control simulation. Sea level pressure is in the black contours. Simulated radar is shown in the shading. Here's the heat wave region in Washington and Oregon. And if you look at this sequence of events, here's this atmospheric river, there's heavy precipitation and very heavy orographic precipitation. In fact, it was a record-setting precipitation event over Southeast Alaska and in northern British Columbia. So in the trajectories, again, from the WRF model, this is kind of a 3D visualization of those trajectories, back trajectories from the heat wave region. The model predicted temperatures in near the 2-meter temperature up to 45 Celsius, and that's close to what was observed in that area, which is again off the charts. When we turned off, just going into the model and turning off condensational heating, it got a lot cooler. It was still a warm day. You still had solar radiation and a warm air mass in place, but you go from 45 Celsius and you cool it by 10 to 15 degrees Celsius. And so it was no longer a record-setting type event when you turn off condensational heating. But I don't like to do that because when you turn off condensational heating, you're telling the model that it has to violate the first law of thermodynamics. And that also really artificially dampens vertical motion because rising saturated air is releasing heat, and that helps with its buoyancy. So I thought, well, let's try a gentler experiment. But just before I get to that, if you look at the upper level ridge in the control experiment, 590 meter bar height, really impressive anticyclone. When you turn off latent heating, you still get a pretty high value of height, but the anticyclone is less pronounced and it's shifted to the south and west and not as intense. But it's still there. But I thought, well, let's let thermodynamics work and not turn off latent heating, but let's just dry out the initial upstream atmospheric river and see if that works. So I just went into the initial conditions and I just applied drying of the relative humidity at the initial time and then reran the model, but with relative humidity lowered considerably across the Gulf of Alaska. And when I did that, this is the simulation that resulted. You see, you still have all this precipitation and heavy precipitation across Southeast Alaska. And that's because a lot of the moisture comes in through the western lateral boundary condition. I said, let's also try drying it even more. And so I did another simulation where I dried out even more, but I still got the atmospheric river. And so I said, well, if I really want to do a number on this atmospheric river, I need to dry the lateral boundary conditions also. And so I did a run where I dried out the initial conditions and the lateral boundary conditions. And I still get a little bit of precip because you're still getting fluxes of latent heat from that warm ocean temperature anomaly. But I succeeded in weakening the atmospheric river. And so that should allow us to test this hypothesis about the Chinook flow. So here's my control simulation, just kind of looking at the sea level pressure and simulated radar for these different runs. By the time you get to my driest run, it's looking a lot weaker. If you look at the average, not the average, but the storm total precipitation, it's a little hard to see, but this is Alaska. So this is the northern Gulf of Alaska here, and this is the control simulation. Look at, so if you average over this green box, you get 26.6 millimeters, but the maximum in there is 372 millimeters. So that's extremely heavy precipitation over 6 days. But with each of these experiments where I dried the initial conditions and dried them a lot, and then where I also dried the boundary conditions and dried them a lot, you gradually weaken the maximum precipitation to the point where the driest simulation you've reduced the average rain by about a factor of 5 and the maximum rain by a little more than a factor of 2. So if our hypothesis is correct, the rainfall in this upstream area should co-vary with the 2-meter temperature down here in Western Washington and Oregon. And so that's kind of what we would predict from these experiments where I've gently dried out that upstream atmospheric river. And if we look at the experimental results for 2-meter temperature, the second and third runs didn't change much. They were both a little cooler than the initial one. But then when I dried out the boundary conditions a lot, you see significant cooling both in the area average temperature and in the maximum. So that appears to fit with our predictions. And if we look at the correlations between the area average upstream precipitation and the downstream near surface or 2-meter temperature, you see strong correlation between the amount of rainfall. And if you look at the maximum upstream rainfall versus the 2-meter temperature, it really falls in a line. I look at this and I said, that's almost suspiciously good agreement. I would almost be skeptical of that because how often do you see 0.99? But there's a strong correlation in any case between the upstream precipitation and the downstream near surface temperature, which is consistent with this sort of Chinook mechanism. The upper level ridge also sort of behaved as you would expect. So when you weaken the upstream condensation, you're also affecting the upper level anticyclone. So you can't really disentangle that from the kind of Chinook aspect. So this shows kind of the control and the driest simulation, how that upper level ridge weakens and shifts like it did, a bit like it did for the no latent heating simulation. But so, why does it matter if this was a Chinook mechanism or not? And again, shouldn't we be keeping in mind the method of multiple hypotheses where, there's multiple factors that are contributing to this event? But I'm kind of focused in on this Chinook type aspect. And the reason it matters is because of climate change. And so I'll talk a little bit about that here at the end. When this event happened, the World Weather Attribution Project immediately sprang into action and concluded that the Western North American extreme heat would have been virtually impossible without human-caused climate change. And they were kind of looking for nonlinear interactions, and they were saying, maybe a couple degrees Celsius of this event was due to anthropogenic global warming. But they basically said the event would have been virtually impossible without it. So that was their sort of initial viewpoint. That's since been published by Philip et al. 2022. But there's more. There was a map, the Albany map list. Some of you may be on that, where there's kind of constant discussions about ongoing weather events. And one esteemed colleague said, okay, the Pacific Northwest has warmed about 1 Celsius during the past 50 years, which we could say that's due to global warming. But the anomaly in this event was 15 to 20 Celsius. So how could global warming be the cause without some extreme amplification mechanisms? And then there do not appear to be any viable amplification mechanisms for global warming that could explain what happened. And this has since been published by Professor Cliff Mass and colleagues in weather and forecasting. And from their abstract, this is a quote, although anthropogenic warming may have contributed as much as 1 C to the event, there is little evidence of further amplification from increasing greenhouse gases. So there's sort of a difference of opinion. There's that, and then there's Philip et al. 2022. So it's interesting. Now with this Chinook mechanism, I pointed out there was the sea surface temperature anomaly of a couple degrees Celsius, kind of in the source region north of Hawaii, where these low-level trajectories were originating. So if we just took the 2-meter temperature kind of in our initial air parcel exercise and subtracted off 2 Celsius and kept the relative humidity and the pressure the same, and kind of went through that same thermodynamic exercise with, say, with a skew T diagram or with just the first law of thermodynamics, you find that 2 degrees of cooling in that upstream region would give you almost 3 degrees cooler in the downstream region. So there's this implies that there's a 45% amplification from this latent heating that you get in this situation. And likewise, if you go the other way and say, well, let's look at end of century RCP 8.5 emission scenario, which shows about 3 Celsius of warming in that source region. If you, again, warm by 3 degrees, assume constant relative humidity and the same pressure, and then go through that thermodynamic exercise of lifting moist adiabatically and descending dry, you find that 3 degrees Celsius becomes 5.1 degrees Celsius, which is a 70% amplification of the warming due to the latent heat being realized in the lee of the mountains. So it's interesting, and that leads you to say, okay, if you're looking at climate change, you have to think about the role that latent heating plays in these extreme weather events. And there's a really nice paper by Song et al. 2022 in the Proceedings of the National Academy, where they were really singing the praises of equivalent potential temperature as sort of the global warming variable that we should all be looking at. And if you look at how theta E changes with warming and how it changes as a function of temperature, that's sort of accounting for the added weather fuel, because theta E, of course, includes the latent heat energy in its formulation. If you look at the Clausius-Clapeyron relation with this exponential increase in saturation vapor pressure with temperature, that mirrors the change in equivalent potential temperature. So what I did here is I isolated the moist component of theta E and differentiated with respect to temperature, and then plotted that. And you see that same kind of exponential increase, showing you that we're in kind of the steep part of the curve in terms of the increase in theta E. And the Song et al. 2022 paper showed, using end of century RCP 8.5 conditions, what does that surface theta E change look like? And you see your Arctic amplification like we're used to seeing, but now what you also see prominently is in the tropics, you have this huge increase of theta E. There's your weather fuel ramping up. And so now, instead of focused on Arctic amplification, you're looking at the latent warming that's been added in the equatorial region. So that's, this picture on the left, which is your RCP 8.5 2-meter air temperature change, looks really different than the theta E changes. You still have the Arctic amplification, but you see in the tropics where the vapor content is increasing the most, that's really where you see the big change. So to summarize, see, I guess I'm running a little bit long, but we started at 2:02, so I'm not too bad off. But I'm not saying that it was only a Chinook mechanism. There were several processes that contributed to that June 2021 heat event. But the kind of upstream condensational heating is important both for the upper level anticyclone, but also for sort of this trajectory-driven Chinook or Foehn interpretation. And also, it helps call into focus the upstream sea surface temperature anomalies that were associated with this event. And so there's this diabatic connection. And when we weaken that, then you end up with reduced downstream extremes. And so I think that there's ample evidence, both from the trajectories, but also from these model experiments, that upstream sea surface temperature anomaly and kind of the Chinook or Foehn type mechanism contributed substantially to the heat in this case. And also the extreme rainfall over Alaska was connected to this event as well because of that strong correlation between rainfall up in Alaska and the heat down over Washington, Oregon, and British Columbia. So, modest, well, 2 or 3 Celsius is not exactly a small sea surface temperature anomaly, but that's giving you this amplification mechanism. And when you get atmospheric rivers and these Chinook type flows, especially in June or September, these shoulder months where you still have strong dynamical forcing, you could see a number of heat events. And now that I've sort of been thinking about this mechanism, I've seen it happen several times. Even the Yellowstone flood case was followed by extreme heat in Texas and Oklahoma, et cetera. Those are kind of more traditional Chinook type flows. It's also been studied in Antarctica. There's been several papers coming out on this recently. Cape et al. 2015 looked at some of these Antarctic extremes as being associated with atmospheric river events that has that same kind of diabatic connection. So when you have an oceanic extreme, that can lead to an amplified atmospheric extreme with downstream impacts. I'm probably out of time. I should thank John and the University of Maryland for inviting me to share this work with you. I've included some references here as well. And with that, I'd be happy to take any questions. Thank you.
Thanks, Dr. Lackmann. That's a nice talk. The attendees can raise your hand, unmute yourself, and ask any question you might have. You can also chat us the questions if you don't have a mic.
Maybe it was okay. I see
Louis,
Louis has a question. Great.
Oh, first of all, Gary, great talk. I mean, really exceptional. When you just at the end, you were trying to look at other cases and other extremes. I've always been struck by the 2010 Pakistan flood that was downstream of the major Moscow heat wave, and there was an incredible ridge that cut off over Moscow, which is probably a study in and of itself. But then downstream of that was the digging trough that then locked in over Pakistan. And this was, an incredible flood. I mean, 20%, 30% of the country was covered. And they've had worse since then. But if you're looking for another case, I'm good. As you know, I'm good at throwing cases at you. That might be one that you want to look. That's point number one. Point number two is I was struck by the Northwest heat wave by its predictability, by the operational models. It was really an amazing set of predictions, which got really the whole area, from the heat wave perspective, opening up cooling centers where they never opened them up before, like in the state of Oregon, and then the fires afterwards. Do you want to say anything about the predictability aspect of these things? Because even that Moscow to Pakistan flood was predicted days in advance also. So
Yeah.
I just throw that out at you if you wanted to talk anything about the predictability of these things.
Yeah, no, thank you. Yeah, great questions. And yeah, as you know, the last thing I need is another case study to do, but
I'm sorry.
no, it's a great suggestion. And there's been other papers that have linked the flood and the heat wave. I want to say, I feel like apologies if any of those authors are on this call, but I know that there's been papers that have linked the flood and the heat in other studies. And you're right, and you're also on the Albany map list. And when this event came into the model forecast window, the first comments people said, "Oh, the GFS is broken.
Right.
It's
Yeah,
forecasting 110 degrees in Seattle. That it's got to be out to lunch." Because it had it, at day 7. I mean, some of the work Greg Hakem has done using some of the AI models, looking at real long predictability windows for this event. But the operational models had this one dead to rights. I remember calling up my parents, who at the time didn't have air conditioning. I said, you've got to go over to my sister's house. And they're like, oh, no, it's never that bad here. We'll be fine. On day 2, they went over to my sister's house. But I was warning them days in advance about this. So it was remarkably well predicted. And, the signal was really strong. The forecasts of the upstream precipitation, I think, were also excellent. So I think the predictability probably hinged on the ability to predict the precipitation in that upstream atmospheric river. But yeah, it's amazing that an event this extreme could be this well predicted, especially at such long lead times. So it was a very robust anticyclonic wave breaking event. And so I gave a similar seminar before and had the same question: how well forecast was this, given it was off the charts? The fact that the models did this and we questioned them, and then it verified, I think is just a remarkable testament to how far we've come with numerical weather prediction.
And one last comment, you made that thing about, would you guess Arizona versus Alaska, right? I was walking around saying this is because Arizona and the Southwest with the ridge building in the first place got into a heat wave. And I thought that this was just, a mechanism that was that heat dome effect, But anyway, I was glad to see these back trajectories, really nicely done. But nailing this thing down to coming from the north, I think was really beautifully done. So thanks again.
Oh, thanks. Yeah, and I know you've been doing trajectories a lot longer than I have. Let's see, Michael.
Hi, yes. Great talk. Thank you so much. I'm with UMD Geography and NASA Harvest. And one issue we're looking at in a lot of different contexts, like drought monitoring, ENSO forecast, crop insurance, is how to deal with products like a drought classification that might be based on a baseline that is non-stationary, where there's a warming trend, and perhaps the baseline doesn't fully account for that. And how does that impact both the classification and sort of downstream, other products or decisions that might be based off of that classification? So it sounds like in the example you were just talking about, the heat wave in Washington, even though it was extreme and sort of way outside the norm, it's still predicted well. Have you generally found that the case, or do you think there are certain instances, perhaps in downstream effects, where the extreme events are very difficult to model their impacts because they're sort of unprecedented?
Yeah, that's a great question. And I don't claim to have a complete answer to that. I think some of these extreme events are better forecast than others. It kind of depends on what part of the parameter space you're operating in, and the initial conditions. But the models have gotten better at forecasting extreme precipitation. So if you get the extreme precipitation event right, then you're going to account for the heating and kind of the dynamical after effects. Now, if it's an AI model you're talking about, that's going to be much more sensitive to the training database. And so when you get an unprecedented event, you know, and this is not my area of expertise, so I probably shouldn't even say, but you know, I think that for a dynamical model, you almost have a better chance of getting it when it's an unprecedented, at least unprecedented with respect to the training data. You have a better chance of getting the forecast right with the dynamical model than with the AI model that doesn't have kind of the physics in it. But you know, I don't know in general, if you look at these other extreme precipitation events, or even Helene, you know, Hurricane Helene was very well forecast. If you look at the high resolution ensemble forecast system, or even the GFS, you know, the rainfall with Helene was forecast really well days in advance. And so I don't know, I haven't done an inventory, but for several of the cases that I've looked closely at, it's been amazing how well the operational dynamical models do, even at multiple day lead times. But as far as the non-stationarity of the data, you know, that's why they're developing things like Atlas 15, and I think people realize the need to have a non-stationary baseline, and I think you know, whatever you want to call it, you know, you can, you know, have to dance around the politics sometimes, but you can say non-stationary baseline without getting into trouble, probably, no matter what you're doing. But I think that's a great point, and that's what we need. You know, we need to understand how the extremes will change, because that's really the cutting edge of climate change.
Awesome. Thank you.
Yeah, thanks for your question.
Any other questions? Again, you can unmute yourself or type it into the chat.
Okay, well,
Yeah, I was trying my wait time. You know, so but thanks everybody for coming. Thank you, Dr. Lackmann, for your talk. It was really interesting. I hope we all learned something new today. I certainly did. And then stay tuned for our last two seminars of the semester. It'll be next Monday and finally Monday the 12th. Next week, we'll have Dr. Travis O'Brien from Indiana University speaking. So with that, again, thank you, Dr. Lackman, and everyone else. Enjoy the rest of your week, your day. Sorry. Take care, everybody.
all right. Yeah, thank you again. And thanks you all for being here. Appreciate it. All right.
Bye-bye.
Bye.